Hello again. Uh, it was really lovely to visit all of you in Rwanda, and I enjoyed actually teaching there. I was also pleased to see your involvement in the course, and happy to see that you wanted to learn and you were somehow trying to learn the concept, asking questions, digging into the topic, which is really good. And I hope that you will keep this enthusiasm throughout the course. So far we have discussed about the descriptive statistics and graphical plots, graphical ways to explore data, something about hypothesis testing, what type of hypothesis we can make about testing means, for instance, and how can we do that? How can we decide about those hypotheses? So it was really lovely. I was looking into your assignments today, and I made some comments. You will, or you might have received my emails so far with my comments. And tomorrow in the seminar, we can discuss one to one as well. What are the mistakes and what you should not be doing again? But no problem. Keep trying at least, and then don't fear about mistakes. Try to think as much as you can, and definitely this will help you to learn more. So the topic today, which we are going to discuss, is the analysis of variance, which is famously known in statistical literature as ANOVA. Today we will be focusing more on one-way ANOVA, and you will see soon what it is meant by one-way ANOVA actually. So we move on. Well, before we move on to today's lecture, as I said, I discussed earlier, let's spend a minute or two to ask a few questions to ourselves. Have we understood hypothesis testing? You can ask yourself and reply honestly, and also, reply to you at least. And if you haven't understood properly, then I would suggest you to go back and look into the notes again. Try to learn them, because that learning is essential in this course. Let me tell you very honestly. We discussed some statistical ways to do in SPSS. So you think you are comfortable with that? If not, go back to my lecture notes. Go back to my assignment number 1. Try to learn, recall what we discussed last week about SPSS. So these are the things which we were learning. Testing for means with unequal variance. Well, I said it is on the whiteboard, but the idea is that if I get time, I will explain this tomorrow to you in the seminar. Otherwise, like whenever we have more means, for instance, more variables to test together, we can't do this by doing the traditional hypothesis testing which we discussed last week. So we have to go a bit further. That's what we will learn in this lecture today. Yeah, last week we learned about a method of testing two means. Remember, we were comparing two variables altogether. Mu1 is equal to mu2. Blood pressure before treatment is equal to blood pressure after treatment. Impact of drugs on patient in week 2 and impact of patient on week 4, for instance. We were comparing two groups altogether, and we were interested in knowing whether they are equal or not, right? But in reality, there are either more than two means or level of interest to test, or there are several factors. For instance, I want to compare all of them together and see whether they are equal or not. I'm not interested in like making pairs. I want to test them together, and there are many factors involved in my experiment. So what should we do? Then t-test does not directly apply. So we go on to the analysis of variance, which is an appropriate tool for these type of experiments. This method was developed by a famous mathematician, R.A. Fisher, in the early 1920s, and it is extensively used in industrial experiments or in industrial settings a lot today. Despite the name analysis of variance, it can be used to compare means, right? So the idea will be to compare means, but somehow we will be utilizing the concept of variation in the whole overall experiment to evaluate mean. And that's why it is known as the analysis of variance, so to say. See, the hypothesis of interest would be that all population means are equal. It means I have like k factors in my data, I have k variables in my data, and I say that all of them are equal. Right? I'm not, notice that I'm not focusing only mu1 and mu2. I'm saying all of them together. I have more than two factors now. I want to compare them all together. Like no factor effect. There is no variation in means among the group. All of the, notice here that there is no variation in means among the group. All the means in this group are same, right? This is my null hypothesis. So my alternative hypothesis would be that at least one of the population mean is different. Like not all of the population mean are same. At least one of them can be different. They can be, all of them can be different as well. But at least one of them means that I put a minimum requirement, the least requirement for the hypothesis to be an alternative hypothesis, which is that not all of the means are same or they are different, but at least one of them is different, at least. And there is a factor effect. And by what I by I mean by meaning that all the means are different, since there are k factors involved, there are k variables, k somehow you can say k variables are involved in this experiment. So I say that there is an effect of difference in variables, right? So you say that you have drugs, for instance, applied to, so you have three drugs applied to different patients, for instance, not two at least, and you wanted to see whether drug number one, drug number two, and drug number three, they have an impact on a patient or not. So you say your hypothesis is that all of these three drugs have no impact. There is no factor effect. There is no drug effect in this experiment. It means all of these drugs have same mean. So this is my null hypothesis. But alternative would be that drug has some effect. So drug is a factor in my experiment. And these three drugs, since they are different drugs, so they have some impact. It means their means are not equal. So these type of experiments, when we do with more than two means, we go to ANOVA. We go to evaluate, well, right now we are focusing on one-way ANOVA. So let's say one-way ANOVA, we resort at this method and then try to use this to answer this question. So it sometimes says that all means may not be different at once. They may not be different at the same time. Some pairs may be the same, but there must be some difference among the pairs. Right? That's why I mentioned earlier that at least one population mean is different. So what we do actually in general to evaluate this experiment, we decide or somehow we decompose the total variation in the experiment. So the total variation in the experiment is the experiment, well, I say SST, which is the total variation in the experiment, which is equal to SSB, the sum of squares of, I said between groups. I use the word B, which means between groups. It means that there are three groups, drug 1, drug 2, drug 3. So what is the variation between these three groups? That's what I mean by here. So the total variation or variation among the groups, right? And then there is a variation among or there is a variation within group. For instance, if I apply drug number 1 to 100 patients, then there is a variation between, or there is a variation among 100 patients as well. You understand my point? So in this experiment, either I have variation between the groups, since I have more than two groups, or since I have lots of patients, so they can be varying a lot with respect to their performance. So that's what I called variation within group. So say variation within patients, variation among patients within group number 1, within drug number 1, and variation among patients when I applied drug number 2, and variation among patients when I applied drug number 3. Because since I have 100 patients, for instance, so they will be reacting differently to drug number 1. Similarly, they will be reacting differently to drug number 2, and so on. So that's why I have variation between groups, because I have more than two groups, and also variation within groups, since I have lots of patients to be treated by the drug. So that's why we decompose the total variation into two parts. So the one of the parts is variation between groups, and another part is variation within group, and if we summed up together, we get the total variation in the experiment. So this is one way to deal with the phenomena of variation or evaluating the variation. So if they are performing similarly, if there is no difference, now go back to think about your hypothesis. Somehow try to connect your hypothesis with this understanding. So if there is no variation among the groups, if all the groups are same, it means variation will be less, right? Because they are same. So if they are same, it means we will not reject our hypothesis, because our hypothesis is that they are same. Our null hypothesis is that they are same. Now we move on. Again, some more description. As I said before, the aggregate variation of the individual data values across various level factor levels. Factors in the drug example is like 3 drugs, for instance. Between groups, again, variation among the factors, and within means like variation exists among the data values. So now I have 100 patients. Those are my data values within a particular factor level, like 100 patients, how they behave with respect to drug number 1, and then 100 patients, how do they behave with respect to drug number 2, and so on. Consider an example, one factor and you have several levels. So an engineer is interested in investigating the relationship between RF power setting and the H rate of its tool. So H rate is somehow related with the metal, the type of metal you are going to use in this experiment or in this study. The objective of an experiment like this is to model the relationship between H rate and RF power. So you wanted to know how much they are related to each other, and to specify power settings that will give you a desired target H rate. So the response variable is H rate because that's what we are interested in. So she is interested in a particular gas, for instance, a gap between between the rates, for instance, and she wants to test 4 levels of power, like 160 watt, 180 watt, 200 watt, and 220 watt. Right? That's what she set up an experiment in that manner. Now the natural question is, how should she proceed to conduct such an experiment? Well, she wants to test. Now go back and see that there are 4 levels of power: 160, 180, 200, and 220. And now she wanted to know how does it behave with respect to H rate. Now what comes to your mind? The next question is, she needs to have a data, right? And also, in order to avoid measurement errors, remember we discussed in lecture number 1 and 2 that sometimes we need to avoid measurement errors. That's why we need more data together. Some of the variables, some of the data points may be rejected. Some of the data points may come up as outlier, for instance. So we need to reject them, and that's why we need more data. So for this particular experiment, again, she has 4 levels, and now she needs data. So what she can do? Well, she can replicate. Replication is a strategy of repeating the basic experiment. So what she will do? Replications help to identify observational errors which might occur during the measurements. Now she has 4 levels, 160, 180, 200, and 220. So she can replicate the experiment 5 times. It means at each level, she will gather 5 data points, right? So now at 160 watts, she will have 5 observations. At 180 watts, she will have 5 observations. At 200 watts, she will have 5 observations. And at 220 watts, she will have 5 observations. Depends on the amount or budget you have, you can even replicate more. The more you replicate, the chances are that you will have less observational errors. But sometimes it's not always possible for us to do replications, or maybe a lot of replications, due to some budget constraints, timings, resources, so and so. So now she has 4 levels, and then each level has 5 observations. So in total, she has 20 observations, right? So what will be the hypothesis? So hypothesis, since we are talking about levels, so hypothesis will be that all 4 levels are same. There is no variation between them. The mean of all 4 levels are same, actually, right? So that will be our the null hypothesis. When I say hypothesis, I'm sorry, I mean by the null hypothesis, actually. Now she has values here. So at each level, Power level, she has 5 observations. These are the observations, and you can you can have like a row total, for instance, and then also the row averages of this at each level, for instance, at each power level. Now we wanted to test this hypothesis. If one is interested, one can even plot. Since you have lots of values, so one can even plot values at each level to see the variation. So the box plot is of course a very good candidate, as we discussed earlier. So this seems to be skewed, this seems to be, well, slightly skewed, this is also slightly skewed, but negatively skewed or left skewed, this is almost normal. So you see that at 4 different levels the behavior observations were completely different. Scatter diagram or dot plot can also be made, for instance, to evaluate or to investigate the performance of observations at each level. Now this is a mathematical structure. I'm not going into detail about that, but if you're interested, that's how we make the observation. Since we are not dealing with 5 or 4 levels in practice, we deal with many levels, and that's why we talk about arbitrarily many values. Say n values, n number of observations at each level. So level number 1, so there are n observations for level number 1, there are n observations for level number 2, and there are total a levels. So that's how we can somehow construct a whole table. And as you see here, all the descriptions which we discussed with the previous with respect to the previous example are stated here, but in a general context. So this is our model. We say that, okay, some constant value, and then mu I is the treatment effect, the level effect, and epsilon is the error. Since we always, in a statistical model, we always consider some error in the statistical model. We always want to reduce that error, but there is always a chance of error. So equation number 1 is a single factor ANOVA model because only one factor is investigated, and that factor is the treatment effect, right? Mu I. So the hypothesis, as we discussed earlier, is that all of the means are same, like mu1 to mu A, since there are A treatments or A levels in total. So all of those means are equal, or in the alternative hypothesis, we can say that they are not equal, right? So this is a test statistics. Remember, we discussed about T and Z test in the previous lectures. So I don't want you to remember those formulas, but for your information, or if somebody asks you, how does it evaluate it? So that's how we can evaluate. Since we are dealing with the variation, notice that it says here the sum of squares of variation between factors and sum of squares of variation within factor. So those two guys are variations. And since we are dealing with variations and it's a ratio of two variations, so this type of thing usually follows the F distribution, right? So it's another distribution apart from the T and Z distribution or normal distribution which we discussed earlier. But you don't need to remember those formulas again, you just need to know the concept. So we will compare our F calculated value with the tabulated value, or we will compare the P value with our alpha to decide, are we going to reject our null hypothesis or we are not going to reject our null hypothesis. So we move on. So we calculate sum of square of total. That's how we calculate those values. Again, you don't need to remember those formulas, like within group and between group, and then in the end we summed up together to get the total variation. Yeah, so it's a classical output. You have values over here so these values in the row wise, they are between levels, and these values in a column wise are between observations. So you plug in all the values over here in these formulas, and in the end you get the F value. So this F value, if this is F naught, is the F calculated, which I showed earlier in the previous slide, and this value was compared with the tabulated value, or we can do like with respect to P values as well. So now in this experiment, I have four levels, mu1, mu2, mu3, and mu4, and I say that they are or equal. Or in the alternative hypothesis, I say that some means are different. They may not be all of them are different, but some of them are different. So I plug in all the values over here, and then I calculate my final result with respect to, or utilizing those formulas actually. So it says that the p-value is less than 0.01. So p-value is really, really low. And you know that if p-value, by the way, we tested this whole experiment at 95% level of significance, which is a standard value. You see here, it's alpha is stated here as alpha is equal to 0.05. So since p-value is less than alpha, which is or you say the p-value is 0.01 and alpha was 0.05, it means p-value is less than alpha. So we reject our null hypothesis, and we conclude that the treatment levels do have some impact. The means of all four treatment levels are not same, right? And they should not be same, because since all those levels are different, if they are different, they should be behaving differently. If they're not behaving differently, so what kind of conclusions we can draw from here? So I chose some levels and I run an experiment, and in the end I test a hypothesis. So I notice that they are different, which it should be, because if they are not different, then it means I need to have there is no point of having two levels with same performance, right? If you want to see a difference, then you should be having a different level. So this indicates that if they are different right now, I'm fine. If they are not, it means I need to pick another level, for instance. So these kind of conclusions we make when we run these type of hypotheses. So here, if you remember, or if you recall my plots which I was drawing last week about the Z and T distribution. By the way, for the F distribution, this is the shape. It's not like a bell shape. It's not like a balanced shape. So this is the shape of the F distribution. And here lies the F naught. Here lies the calculated value. So this value is above or far from that region. This region is the acceptance region. So it's way beyond that level. It means now we are going to reject that value because it's outside that region. So this is the acceptance region, by the way. This curve is the acceptance region. After that is the rejection region. So if the value falls over here, then we are going to reject our null hypothesis. So recall from lecture number 4a and 4b that t-test tells us if the variation between two groups is significant or not. So when we are aiming for two groups, well, we can apply t-test. But when we are aiming for more than two groups, then we apply the one-way ANOVA or the general ANOVA method. But why not just do t? Okay, so now my question is, I wanted to know there are 3 or 4 groups, but I wanted to compare them in pair, right? I wanted to compare group number 1 with group number 2, group number 1 with group number 3, 1 with 4, 2 with 3, 2 with 4, and 3 with 4. That's what I wanted to do. So the multiple t-test could be a good option. But the problem is that it's not the answer, because as the number of group grows, the number of needed pair grows accordingly, right? So if suppose you have 7 groups, then you need to have 21 pairs to evaluate, which can be cumbersome. And in reality, we do have many groups. So what we do? Well, we can apply some different methods. So if we test 20, as I said, if we test 21 pairs, we should not be surprised to observe things that happen only 5% of the time. Thus, in 21 pairings, alpha 0.05 for one pair cannot be considered significant. And also in ANOVA, we put all the data in one test, which is the F test, the F distribution. So it gives us one p-value in the end for the null hypothesis. So what could be a better way? We can use one-way ANOVA procedure to test the hypothesis that the mean of 2 or more groups are not significantly different, right? So one-way ANOVA offers group level statistics for the dependent variable, like testing for variance inequality, testing for grouping of means. We can even plot means, and we can even draw some kind of multiple comparisons. So you noticed that we can't use t-test here, because t-test can be cumbersome if we are going to compare pairs, because in reality we do have lots of groups, or we do have lots of levels actually. So ANOVA can be a smarter way. With one value of one p-value, we can decide, are we going to reject our hypothesis or not. But if you would have thought about t statistics, that could be cumbersome, right? So in SPSS, well, we will be learning more about SPSS when we will be dealing with assignments, but that's how we do that. So we go to analyze, we go to compare means, and then we choose one-way ANOVA, right? Before we were selecting one sample t-test or independent sample t-test. Even sometimes we also selected paired sample t-test. But one-way ANOVA would be our option if we are going to evaluate something like that. As I said earlier, you can even go to help and then statistics coach or case studies, and you can learn even more how to apply ANOVA in SPSS or how to do things in SPSS in general. Once we are done with the ANOVA part, the hypothesis part, we also want to evaluate some like adequacy checking, whether the model is appropriate or not. Because in the beginning, if you remember equation number 1, we had a model like alpha plus mu I plus some error. So in general, we discussed some of these concepts last week as well, but in general, what we want to know, well, we wanted to know whether our errors are normal or not, and also are they do they have a constant variance, or the variance is changing. Also, independence, are they dependent or independent with respect to days or with respect to values? So if you find them, like if the model is correct and if the assumptions are satisfied, then residuals should be structureless. By residuals, I mean errors. So in general, we say errors, but when we run a model, we call them, just to differentiate with the previous term, we call them residuals. So if you run an experiment and you evaluate residuals, make some plots, normality, it should be normal, and also if you make some plots, it should be structureless. There should not be any pattern. By structureless, it means there should not be any dependence also, right? Because dependence is what drives the structure. And they should be unrelated to any other variable also. Residual should not relate to any other variable. There should not be any dependence between residual and the variables. So if we do so, if we notice something, it means our model is good. That's how we decide our final model. So like here, so we can even plot those residuals, and if when we will be working on SPSS, you will see that you can make residual plots like these. So the normal probability plot is the plot for residuals, which tells us whether the residuals are normal or not. So so those values, those squares, these are the values of residuals. So if they are normal, then they should follow this straight line, this line, this trend line they should follow. If the values are on that straight line, it means that the residuals are normal. If they're not on the straight line, it means they are deviating from normality, which they should not be. And if they do so, then we should not consider that model. Sometimes we plot histogram to see if we get a balanced curve, if we get a bell-shaped curve or not. To detect a correlation, we can just make a random plot, a scatter plot, and see if you see any dependence or any structure in that graph or not. And like here, you see that detecting correlations with one way. Also, one can think of like positive and negative residuals, but are there any structure over here? So like it means an independence assumption of residual, if there is a correlation, then it means an independence assumption has been violated. Right now I can see that there is no structure in this graph, at least. Even for homogeneity, you can even see with respect to your values, like predicted values and your residuals, do you see any structure between them, how they are behaving, for instance. So once we are done with the ANOVA comparison and we decided, okay, all the means are not equal, all the means are not equal because we reject our hypothesis, remember that. So the next question arises, can we do some kind of paired comparison to see which of the means are different more and which of the means are different less? You understand my point? So these type of analysis we do in the post-ANOVA comparison. So we say that the analysis of variance tests the hypothesis of equal treatment means. Now assume that residual analysis is satisfactory. It means we are going to accept our model, and we say that our residuals are structureless, our residuals are normal. We do apply those tests in our assignment number 2. So don't worry about that. And if the hypothesis is rejected, we don't know which specific means are different, because there were lots of means involved. We say that they are not different. All of them are not same. But we wanted to know which of them are more different compared to the others. So determining which specific means differ following an ANOVA is called the multiple comparison problem. Now we can compare. We can make different comparisons. And there are a lot of ways to do these particular to answer this particular problem. But one famous way is the Fisher's least significant difference test, LSD test. So in this test, we compare means with respect to t statistic, like here. So we compare each means. So if you want to compare, for instance, pair number one with treatment number one with treatment number two, you compare the mean of these two guys. And then this is the formula, by the way, for that method. And then once we are done, we compare this value with the tabulated value, or we compare p-value again. So like here, so now we have it's a classical output. So you had four levels. We had 4 levels for that particular example. The previous example, remember, 160, 180, 200, and 220 powers. And these are the 4 levels. I wanted to compare them in pairs, like 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. And these are the p-values over here, probability values. And it says that all of them are actually less than alpha. It means all of them are different, right? Since p-value is less than alpha in all of these cases, it means all of these means are different from one another. 1 is different from 2, 1 is different from 3, 1 is different from 4, 2 is also different from 3, 2 is also different from 4, and 3 is also different from 4. Significantly different at 95% level of significance. So we do these things in order to see that whether some of the means are same or some of the means are different. Right? Luckily, in this particular example, we notice that all of them are different. But this may not be the case in most of the examples. And in the future, hopefully, we will see some examples where we differ from that particular methodology or that particular idea, so to say. So right now, we focused on one-way ANOVA. We dealt with one factor that has different levels, for instance, 4 or 5 levels maybe, and we wanted to evaluate their performances altogether. We see, do they perform altogether similarly or not? And the way to do this is through one-way ANOVA, right? So we stop here. We conclude this session for one-way ANOVA right now. And in the next part of this video, we will be talking about two-way ANOVA when we have more than 2 factors, for instance. Thank you very much.